Okay, let us go ahead and get ourselves started for today. It's actually going to be our last class session, and there's a lot of things we want to sort of do to kind of really set you up for where we go next with all this. So we do want to spend some time talking about assignment 5 and really what we've asked you to do and what some of the bounds are on what we expect you to do for that, because it really the problems posed in Design 5 are actually very big problems, very kind of interesting ones to think about that are much larger than the assignment. So it's always a little bit difficult kind of just scratching at the surface of an issue without really digging in very deeply. But the intent is not to dig in very deeply because, at some level you could write an entire thesis on the very simple questions that are sort of posed in that assignment. And that's not the intention at all, is for you to go that level, that deep. We're also going to spend some time today, just kind of finishing up just a couple of examples of that whole recursion thing and really how we can nest different loops as just sort of a way of approaching optimization. But I want to dig into the whole notion of really, different ways of evaluating and looking at multivariate optimization. And for that, we'll look at some papers and some research that's going on. It's really a very emergent field. There's a lot of attention on really what we can do, because we now have the ability to evaluate all these things. Before, we didn't have the ability, so we made simplifying assumptions and we tried to just parse the problem down to something that would be very easy to solve. Now, through all the power available in the cloud to analyze all these things, we sort of feel like we have an obligation to consider all these and really find true optimal solutions. And it begs the question then of really, how do you trade off 5, 6, 10, 20 different criteria, and really figure out, is there a true optimal, or is every optimal somehow contextually narrowed to some specific thing you're trying to accomplish on a project? It really gets down to what the objectives for the project are. And as we do that, you'll find that really every project has a whole series of different stakeholders, and they often have very different objectives. So it's really hard to say what the overall best is for the project, because it really depends who you ask. But we'll talk about that. We'll also talk about this whole notion of really the computational design community and point you towards sort of different places to go and resources, and hey, if you like this stuff and this is the sort of community you'd like to get involved in, like where you go and how you plug into all that. Because it's really just the beginning in terms of doing all these things. So to get ourselves started, what I'd love to do is just take a look at assignment 5 and just kind of dig in there a little bit, but just kind of ask how it's kind of going for people in terms of kind of approaching it. So here's the assignment. It's due tomorrow at midnight. And again, it's intended to be something that is, some sketching and some thinking for a few hours, but it's not really a big programming assignment. And the idea is really that at some level, it's all about kind of thinking about different criteria. At any time, it really always comes down to, in any project, understanding what the needs and desires are of the stakeholders are, figuring out which things are fixed, which things are variable, and typically we can choose, which ones we want to hold fixed and which ones we want to kind of explore as variables, figuring out what it is we want to optimize, and then ultimately we have to define measures. That's always the hard part. It's really, how do you measure these things, and ultimately how do you compare these things? And that's where the real artistry comes in. At some level, Dynamo, Grasshopper, all these tools, they can help you compute things, but that's only half the answer. Really, what you do with those numbers is really where the artistry comes in. So we want you to think about really, it's a couple different criteria, and you can choose the criteria. We suggested possibly looking at the notion of cost, looking at the notion of sort of overall performance, maybe an aesthetic criteria, but it can really be any 3 criteria you want to be looking at. Okay, and the idea is to really say that for these different criteria, have some rubric of really what is going to be a better performing and a worse performing shape or form for each of those different criteria. And then go through and just really illustrate how that would apply like this in different forms. So the idea is to choose some different shapes and then just kind of sketch out really, what a building would look like if it was optimized for each of those different criteria. Okay, so let's do this just as a reality check, because I know some people have worked on it. Some people probably haven't had much of a chance to get started with it. But let me just, for the folks here in the room, kind of just do a little reality check in terms of the type of criteria that you're looking at or that you're thinking of looking at for this assignment. And let's see if we can just kind of play them out a little bit in terms of, trying to understand really what we might get to and what a reasonable solution relative to assignment 5 would look like. So, in terms of like the criteria that people are looking at, like Natasha, do you have sort of can you suggest a criteria that you're looking at, one of the ones that you're considering?
Well, that's right. With structural performance and type of material applied, that if the building should be really sustainable, the material should not be. For example, if there's a lot of clay in the area,
sure.
The main structural material should be clay, not steel.
Okay. So within structural performance, one thing we look at is just the amount of local material. And as we looked at that, and for all the different materials, it's sort of a good lead criteria to, we could really, we could evaluate really the percentage of the local material, or we could go through, we could do that as a percentage. We could say that, we're going to, for every different element, somehow weight it by how unlocal the material is, where things that were very, very local and indigenous, they got a very favorable rating. For things that are very, very far away, they get a very unfavorable weighting. And somehow we're trying to have the smallest kind of value, for the smallest local value or the smallest, So we could go do a sort of a weighted value, and there's a lot of ways we could go through and approach that. And that's just
connected thermal performance.
Okay.
Of the wall, but it's also related to material.
Sure. Sure. And then there's this funny trade-off between the two. So in terms of thermal performance, how are you thinking about that? In terms of just the amount of energy used, or what are we thinking about it? Okay. Sure. So these are all sort of like inputs. We can vary the amount of insulation, things like the temperature and the seasonality sort of things. Those are sort of more givens just for the individual location. So how are we ultimately going to measure that? How are we going to decide whether it's good or bad or optimal? What do you think is sort of a good way to think about thermal performance?
First, we have to define what is the structural performance to shelter different issue of building.
Now this is okay. Okay, so you're giving a sense of hierarchy to it. Okay, so we need to basically have a good shelter first. It has to sort of work at that level, and then we can start thinking about.
It has to be warm or cold.
Sure.
At optimal temperature. So this means if material needs additional insulation, or we should define the thickness of the wall, maybe without needing additional insulation. I don't know.
Sure. Sure. So in terms of looking at this, we could say there's this energy use intensity. That's sort of one way of looking at it. We could go ahead and say that, great, just for that's all about just basically the amount of energy per square foot per year. So we could, for different assumptions here, rate it, and we can sort of figure out really where we want to come there. The interesting thing about energy use intensity, even sort of thinking about it, is, again, there's always this funny trade-off. I could try to have a very, very good energy use intensity, really minimize the amount of energy. It's going to lower the operating costs, okay? But that may actually start having a very high production cost, because all that extra added insulation in the walls, it may lead to a more expensive construction system. It may just be, it may end up sort of using some materials which are sort of bad because we're consuming more materials, but good in the sense that it's going to ultimately save over the life cycle of the building. So or we may be trying to use materials which aren't so environmentally recyclable or have bad carbon footprint. There's a lot of different trade-offs in there. So it's just a complex space.
And then we increase, for example, with the size of the room. So we see energy performance and how the room is used.
Yeah.
And if these structural performance reports are only of a specific
Mm-hmm.
then it has impact on the room that is imposed from outside.
Sure.
And this is only one small segment of a building.
Oh, exactly.
Room could be different, and then I don't know, solar came and it looking on just one wall.
Sure.
A room.
Sure.
And then we have to look at the whole program, how many rooms we need depending on the function of the building and the size of the room.
Oh, sure. No, actually, let's talk about it. So this is you're thinking the whole holistic system. This is good, yeah, because it's really at a high level. We need to approach it that way. Let me pull out kind of a narrower example, okay, relative to just that sort of the shape that is really, it's sort of related, to this, but it'll sort of just make it, just a smaller problem because this is a big problem in terms of really ultimately figuring out all these things. For example, one of those things is this whole notion of, it is that whole sort of solar insolation, blah, blah, blah. And as we're thinking about the whole notion of solar insolation, and here's the sun kind of hanging around in here and it's projecting its rays down, and here's our building. Okay, and I'll start with this sort of a very simple building. It's really, there's this whole issue about really what we can do if you were really going to go ahead and take that building and just this type of form, and if you were really trying to maximize the solar insolation because you wanted to go ahead and just really have the most ability to go through and collect energy through solar panels or something like that, what sort of things could we do to that form if you were really looking at that, independent of any other criteria? Like, what would we want to do to the form? Sure. So how can we do that? What are the things that are going to sort of maximize its exposure to the sun? Oh no, very good, very good. So it's interesting as we think about the solar potential of the building and stuff like that. There's lots of different things we could do. We could say, I want to make a very low flat building that's going to have a big roof, because roofs tend to be very good collectors for the sun. They're just unblocked. They tend to get a lot more sun than the sides, actually, just because of the way the angle of the sun is in the sky and stuff like that. So we could go that way. Another way you could go, which is really very interesting, is we could say, let's go ahead and make a building that looks more like this. Where, as you suggest, really what we're trying to do is really have this angle pretty much match kind of perpendicular to that as much as possible. And it turns out that'll actually optimize. Doing something like this, we have a big flat roof, that basically says, give me a lot. And even if the angle isn't the most efficient angle, I'll still make it up in the end. This over here says, no, I could have a small amount of area, but per square foot of area, that's going to actually maximize the amount of collection. Now, either one of those, if I looked at it just in terms of the solar insolation, those, one of them might be better. They might actually be relatively equal. In the scheme of things, though, as you put it all together into a bigger system, as you suggest, though, it all starts tying together in that, this may not, it may be pretty good. Maybe I need a lot of area, but this is probably a relatively inexpensive building to build. And probably has pretty good characteristics in terms of the amount of square footage and stuff like that. A building like this, which is very, very good from the solar potential standpoint, it's a little more complicated in terms of the structural system and just how it's all working. So at some level, we could be sort of raising our solar insolation potential, but at the same time, increasing the structural complexity and maybe the structural cost. Maybe there's there might even be more materials involved in terms of doing that. So again, it's sort of this. Oh, exactly. Exactly. So the thing about this that we really, want to do for the different shapes is, in the assignment relative to it is really say, okay, great. Whatever criteria we're looking at, whether it's the solar insolation or whether it's something about the energy performance, we just really want to sort of play that out on different shapes of buildings, okay? And really kind of talk about that kind of, at a high level. So in terms of shapes of buildings, and again, no worries, you haven't started on it yet. because there's still plenty of time to get it done. Like this sort of rectangular building shape is one that I keep on using because it's easy and stuff like that. Let's think about how some other building shapes play out. I sort of suggested a U-shaped building or an atrium building or an H-shaped building. When I say those things, does that sort of make sense to you in terms of the different types of shapes of buildings? Okay, so if you're looking at, let me give you a U-shaped building, something that looks like this. A little off, it'll work. Okay, as you think about a U-shaped building, what is different about a U-shaped building as opposed to kind of a rectangular building? Yep, a lot more surface area. Okay, well, think about that. What is that bad for? Okay? Yeah, well, it's in terms of because of all the surface area, we have a lot of surface energy rolling out in terms of what's going on. Doing something like this, it's the whole solar characteristics are quite interesting in this in terms of we have a little less area up here. A lot of the surfaces are heading kind of in a funny direction. Yeah. Sort of what is it good for? Like, why do we do buildings like this? Yeah, ventilation's a very good thing. What else are they good for? I'll say shading's actually not such a bad thing. That's very good too. I'm going to add daylighting in there, but now you actually have, it's just like there's sort of this function. They're really, it's quite interesting about, really, what happens in that interior space, because it actually is kind of a nice protected space. It's sort of protected from the wind. It could have an awful lot of kind of good affordances. In fact, the variation of this shape, which is kind of interesting, is, the Courtyard building. Yeah, let's talk about Courtyard buildings. Why do we build Courtyard buildings? They have a big historic precedent. What were Courtyard buildings good for? Like if you go to Pompeii, you go to New Orleans, you go to a lot of places in the world. Courtyard buildings are a very common form. They usually look sort of like this. So what's a courtyard building really good? There's kind of a social sort of thing going on in the courtyard. Yeah. They got a lot of precedent. One really interesting thing about courtyard buildings is, they're very easy to defend. Okay, so you pretty much have one entrance, and if you manage to defend that, you sort of have this option of you have basically kind of a relatively limited amount of vulnerable space. Okay, but at the same time, because all these spaces open to the courtyard, like all the space around the courtyard has this perception of being very open. The rooms get daylight, the rooms sort of get ventilation, but at the same time, they're not really vulnerable to the attacking enemy or robbers or anything like that. So there's kind of a reason we like courtyard buildings. It's really but again, it's designed to optimize a certain thing. Having a building like this, if I am in a very defensive position, this might be a very good thing. It's not so great for ocean views. But on the other hand, a building which is incredibly open, like a building like this is actually sort of very vulnerable. It's really, there's a lot of exposed surface, whether that's vulnerable to the environment and wind and solar or vulnerable to attackers. It's all those different things. So at a high level, for this assignment, it really is as simple as just saying, for the criteria, how would you change the shape of those different buildings? For example, if I had a courtyard building here, okay, And I really wanted to go through, and daylighting was one of my criteria. If the distance away from any, like lighted surface was the criteria, I could say that really for my courtyard building, I really don't want to be this narrow. I really have to make sure that the size of the courtyard allows that really this distance over here is no more than some tolerable distance, from that, whatever is considered the good distance from the, the outside light. In the same sense for this H-shaped building or this U-shaped building, if I really want to go through and use daylighting as a criteria, the shape is almost sort of dictated by this, and this is actually, where a lot of these buildings got shape from. What you have is typically, there's some central corridor. Okay, and they typically don't worry about that being lighted. But these buildings are almost always basically 2 rooms wide plus a corridor. And that's really how it all kind of comes together. Yeah, it's interesting. Here in Y2E2, we sort of have this thing, it's a combination of these different building forms. We have these atria, which are trying to bring the daylighting down into the spaces there. We're really, what are we? We're sort of, we pretty much have an outer wall on either side. Then we have an inner wall. Okay, so all the offices are out here on the outside. All these core functions like bathrooms and classrooms, we're stuck here in the middle with pretty poor light and all that kind of stuff. But they tried to compensate for that by saying, okay, what we're going to do is we're going to put an atrium in here to at least bring light in here to these spaces on the inside and do it kind of an interior function. But it's really, the overall shape is really dictated at a high level by this notion of daylighting, because it really was this whole issue that, we wanted to get daylight in from this side, daylight in from that side, and then really how far in could it bounce? So these are really shaped more like daylighting and environmental considerations than anything. Okay, but for the assignment, all we really want to do is just, say that for these different shapes, okay, really, if you were optimizing the building for that shape, what would it look like? So my atrium building optimized for daylighting looks like this. Okay, what would my atrium building look like if I was, instead of optimizing daylighting, if I was optimizing sort of this notion of, surface area or something like that? Or if I was, what else could we do?
Evacuation, fire regulation, instance of evacuation of people like distributors.
Sure.
So it means points where staircases can be, and do this in a room with the best optimal structural system.
Exactly. So it's interesting because what you're suggesting, which is really good. So I'm going to put the kind of hold the sort of fire evacuation right in here. It's kind of again. Sure. To the egress. Okay, and this is, but there is sort of a hierarchy to it. So what you're suggesting is that, hey, let's figure out the structural performance first and then go from there. And that's actually, in a way, that's the same model they use with like the Shanghai Tower. That overall form, more than anything, was really dictated by, they had to choose one thing. They chose wind resistance, because that was the biggest impact on the cost and the ultimate structural performance of the building. So they started with that. After that, they got into different things in terms of the aesthetic qualities, and the building energy performance qualities. But it all started with this whole notion of, optimizing the structural performance, and then within that, they sub-optimized for things like the aesthetics and how big those building envelopes should be in the double wall construction. So let me just get a sense from you guys in terms of, have you started yet? Are you thinking about starting, or as you're going ahead? Because, again, I don't want this to sort of be a big old thing between now and tomorrow night, but I just want to sort of think about, like in your mind, do you have a good sense of how to approach it? Yeah. Okay. Feeling good, Sung Ho? Yeah. You feeling good? No? Hey, everyone? Okay. It's really more, and again, it's go through and just kind of think, at a high level at what's going on in terms of what you're doing. Again, not about the programming. It's really more about just sort of outlining some criteria, a couple lines that sort of say really how that would play out, and then maybe a couple sketches to sort of say what that would look like, if I applied it to a rectangular building, if I applied it to a different shaped building. We're really just trying to get to this whole notion of that you can optimize for the individual criteria, which will take you in one direction, but then if you really want to try to optimize for some hybrid of all the different criteria, it may take you in a different direction. That's the real point behind it, is to really think about, how if you only have one, you can go very hard in a single direction. If you have to trade them off, there's some sort of compromise. And most buildings are that way. They are a compromise. As Natasha suggests, it is this whole notion of, you just sort of decide on a layering and a hierarchy and all those things and how they're going to work together. Okay, beautiful. Let me go ahead and just do a couple things with you in terms of just Dynamo and stuff like that, just to finish up. So a little bit of random stuff, but then really spend most of the time moving ahead into just thinking about the future and where you go with all this. And actually, Patricia, where are we in terms of office hours between now and tomorrow? Is there some more lab hours for people, or what do we got? Okay, so just right after class? Beautiful. Okay, and after that, they're on their own. Okay. Okay. Okay, very good. So we're in good shape there. Then let me go ahead and just kind of illustrate a couple things. In terms of thinking about things and different sorts of ways of programmatically driving, this evaluation, again, this is really subordinate to the whole notion of that ultimately you need a strategy. But if you do have a strategy, it gets back to then how can you implement that strategy to produce the values that will let you test and sort of figure out what the optimums are. Okay, let's just kind of finish out a little bit on that because we got rushed right at the end last time. We'll just kind of talk about two sort of variations. And this is actually a good model as you propose that there's sort of layers to it. And we'll talk about really what's going on in research as other ways of thinking about it. Okay, so what I'm going to do is I'm going to open up at 17.1. It's that little Freedom Tower example. And just sort of finish out the little thing about the recursion as a way of going through and thinking about finding the height. I'm trying to click on that and nothing's happening, and I'll figure out why in just a second. I always type up. My click's not clicking. Okay. Come back over here. So I'm going to illustrate, I'm going to show you sort of two different things, but won't spend a lot of time digging into them. They're available and you can kind of dig into them like on your own. The idea is, again, we have this funny tower here. We were looking at the issue of as we changed the amount of flare at the different corners of the tower, that we still wanted to go through and try to maintain a certain amount of square footage in the building. Okay, and in terms of trying to do that, we might have to actually adjust the height. Again, we could adjust other criteria, but it really gets to sort of this notion of, with the fixed criteria, so what are driving criteria, what are driven criteria? Okay, that's a good way to sort of think about it in terms of your language. And those are things you get to choose. Oftentimes, things like, site constraints and setbacks and different planning restrictions, they can create driving criteria at some level, or just fixed criteria. You can't really change them. They're an outer envelope of really what the availability is. So within that, you get to decide, really what it is that you want to try varying and what you'll try to optimize based on varying it. So this one's really all about the whole notion of, for those corners of the building, can we change the degree of flare, or I call it the flatness on the side, and based on that, somehow try to improve the shape of the building relative to solar insulation or something like that. Okay, so in terms of doing that, the problem we ran into, or the kind of challenge we ran into, was that, hey, at the same time, just changing that is okay, but if we had this notion of we really want to go through and be able to sort of maintain a constant amount of square footage, so that'll again be sort of a constraint. We're going to say that, hey, I need this thing to have around 4 million square feet, so no matter what you do to it, you have to always give me 4 million square feet. And again, that's a choice. Like we can choose other ones in there. We can then use those to sort of start doing our analysis. So the big thing about all this sort of stuff is that as you're going through and driving, you have to sort of figure out really how many variables are fixed and how many you're allowed to vary, because if too many things are varying at the same time, you just sort of end up with a big, sort of mess. It really kind of is hard to sort out. So it's very important you figure out really what's fixed and what's going to be a driver. Okay, so in terms of this, if I go back to Dynamo, where we had left this is we had set up a script to actually sort of play around with the notion of changing the building height to always go through and optimize, or always give us 4 million square feet. So let me go into session 17 and we'll open it up. It's happening under 17.1. Okay, so there's a lot of scripting in here. The big thing that we sort of looked at last time is that in this, there is something called find height for target floor area. That's a recursive function where we're just passing in sort of a starting point, an increment, and the target value, what we want it to come to. So within that, we're going to pass it things like start at 1350, increment by 10, and try to target 4 million. Okay, and sort of always come to that. Now, in terms of why this didn't work last time, it didn't work because as I was doing it, I was sort of already at 4 million, so there wasn't really any iterations to do. It really already was there. So let's go ahead and run it and kind of show you how it looks. Because what I've done over here on the tower, okay, based on a specific amount of flatness, in this case, I have it set to 100 as the distance. So it's about halfway between 0 and 200 in terms of the size here. We sort of have this thing that's almost like octagonal shaped right now, pretty regular in form. If we say start at 1350, go by 10, try to get to 4 million, you'll see at 1300, it's got 3816. Okay, let's just go and iterate through that and see what it'll come to. So again, starting at 1350. Actually, let me start that one even a little bit lower. Okay, we'll run that. What are you doing? There's 1320. Going to evaluate that one. You see at 1320, it basically has 3891. Okay, so it's getting close, but it's not quite there. We'll see what happens at 1330. 1330, 3894. Okay, getting a little closer. Let's try 1340. 1340, 3931. Okay, it's just going to keep on growing. 3969 at 1350, we're getting pretty close. 4 million. Okay, so 4 million. The answer, so 4 million is just over. That's 1360. So we can now get into this whole discussion about whether I want to be the first one over or the last one under. Yeah, because it's either, the answer is either 1350 or 1360, just depending on how you want to look at it. The way we actually design the function is we actually design this function to go through and return, what is it? It's basically the value minus 1. Well, that's interesting. That's showing 1320. I got something goofy going on there in my logic in terms of what's being reported. But it's basically like pulling that value back out. So it basically stopped right there. Now, let's try it a little bit differently. Okay, this is 1360 we're saying is the value if it's 100 in there. Okay, let's change it around a little bit. Let's say the top flat part is closer to 20. So this is a much skinnier tower. Okay, so let's do a little intuition check. Given that it's a skinnier tower, does the tower need to be taller, shorter, or the same? What's your guesstimate? Taller? Taller's a good guess. Don't be shy. I'd guess taller. If it's not taller, I'm gonna work extra hard to figure out why it isn't. Okay, so 1360 we know is already a little shy because it's showing 366. If I wanted to sort of speed it up a little bit, let me start it at 1370. And we'll run that. Again, we'll just sort of let that come through. Hopefully it'll start at 1370. There's 1370, so 369. Okay, and it'll rotate through. And with any luck, if my programming logic holds out, it'll go through and iterate and ultimately get to 4 million. Now, as we're doing all these iterations, it is going through and computing the gross surface area, the volume, all those different things. Okay. At this point in the iteration, in the recursion, I'm not actually gathering that data. I could be gathering that data, but since I only really want to consider the case that actually meets the 4 million criteria, I'm going to wait and do that later in terms of what's going on. I'm really just going through and grabbing the gross floor area and always just comparing the gross floor area to the target value. So let's see where this one comes up. 1410. Okay, it's getting taller. So let's think about this ahead to where we want to go with this. So great. We have something now that'll go through, and for any degree of flatness, any sort of amount of flatness up here, it'll go through and figure out really what the height needs to be to go through and deliver the 4 million. So 4 million's a constraint. You know, we're going to go ahead and change the height to go ahead and match that. So think about how we start working that together kind of at a bigger hierarchy. Because what we would like to do is, if what I want to test, okay, in this whole structure is really, you know, what the degree of flatness is, or really what the, you know, directness values, the desirability, whatever the rating is for each of the different flatness values, okay, what I need to do is iterate through the different flatness values, and for each of the different flatness values, okay, figure out basically what the appropriate height needs to be. And then after I figure out what the height needs to be, then I can evaluate its flatness. And I'm going to iterate through all of those different flatness values. So I'm going to do a little for each. So you get to this whole notion of it's really just nesting things. And that's a very kind of common way of doing things. You sort of have different variables. You have the primary one you're going to change. Then we're going to do a little looping and sub-optimizing within that. Then after we figure out what the answer is for that first stab, we're going to back on off, kind of do it at a higher level, change it to the next level, and then again, figure out what we need to about that, and then keep on looping through that. So what this is going through, it's actually kind of interesting. So it's getting close, but it's actually higher than I thought even. 1470, 1480, I think taller than I would have guessed. Okay, so that height value, it's going to change no matter what the degree of flatness is. Okay, this sort of function would work if we change the tower base. You know, it's a good parametric object because we could change a lot of different things. If the whole issue of 200 by 200 wasn't a constraint, we could go ahead and change that. We can think about making it fatter at the bottom and more pyramid-like as opposed to so tall and spiral-like. But it's really always, you know, what's a driver, what's a constraint, and really what are you checking and reporting on? Okay, so it looks like this one topped out at 1490. So somewhere, you know, we know that really when it was 100 wide, the value was something like, was it 1360, 1370, 1380? It was something like that. Okay, when it's only 10 wide at the top, the value is like 1490. So you can sort of imagine there's some range of values between there. Okay, it's probably not linear because it's not exactly a linear function, but yeah, there's some bounding we can sort of do based on that. And now we're ready to start testing at a higher level. So it starts with this notion of let's just go ahead and use the recursion to go through and compute all the values to get the height right. Okay, and then we're ready to take it to the next step. Okay, and that is if you can pop on over to 17.2. And in 17.2, which is says nested optimizers, let's open that up. I'm not even going to worry about running it because I have no doubt have some issues in my programming logic here, but let me sort of explain the logic to it in terms of what's going on. The idea is here, we have a couple of different types of optimization going on. At the highest level, what I really want to do is take the parametric tower and I want to change this notion, the top flat side, that whole issue of really how big it is at the top. And based on that, I can go through and range through some different values. I'm thinking about really where the increment is and the range of value. Oh, there it is right there. I'm looking at it right there. So I'm going to start with 10. I'm going to jump to 20 and I go all the way up to whether it's 50, 60, or 100, whatever it is. So I'm going to test some different values for the flatness. I'm going to test it at 10. I'm going to test it at 30. I'm going to test it at 50. I'm going to test it at 70. I'm going to test different flatnesses. Okay. And for each of those different flatnesses, what I really want to do is go through and report this evaluation, this some sort of desirability rating, okay, that we sort of looked at based on the faces and the directness of the sun, something like that. So what we're doing is we have this little sort of function right here. It just evaluates all the faces for the varying inputs. Okay, and we're going to do a little for each that's going to range through all those things and ultimately write some big old data file and hopefully find whatever the maximum is. So that's the high level. Let's just go ahead and iterate through all the different values of tower flatness. Okay, within that, when we go looking at that node, we have something that looks pretty darn similar to what we've seen in the past. We're going to set some element parameter. In this case, it's going to set the element parameter to be the new tower height. It's going to sort of get some sort of element parameter, and then it's going to pull out, like the gross floor area and the gross volume, something like that. Okay, but here's where the little mystery action happens within here. Because we're used to, those steps, but we want to add a new step in here. Somewhere between gathering the values or setting the top flatness and the gathering of the values, we have to do this little intermediate thing, which says, given that degree of flatness, go ahead and get the heights right. Figure out what the height needs to be. Okay, and we're going to do that just by putting another step in here. So back in the perform, okay, the first step of the perform was go ahead and set the height or set the flatness. The second step we really want to be go through and figure out what the height needs to be before you start reporting the values out. Okay, so to do that, we just add a second step in here, and I actually have it down at the bottom. And that's really just basically find the height for a certain target floor area. And what this is going to do is for that same object, for that same tower, basically for every different iteration it goes through, like let's go ahead and say, given the tower height and starting at 1300, incrementing by 20, trying to target 4 million, like figure out really, what the height needs to be for that different flatness value before you report. So it's going to go through, this nesting going on. So change the flatness, then within the flatness, figure out what the height needs to be. And we can do it 2 deep, we can do it 3 deep, we can kind of keep on layering these. You're really just kind of controlling logic within logic. Okay, now this thing in terms of running, it takes a while to run and stuff like that. So I'm not going to run it for you right now. We'll go actually take our break right now. But I just want to sort of check in on the notion of, the idea of having this logic within logic, sort of a bigger for each iteration loop, and then for each specific iteration, doing another type of, sub-optimization to figure out what the height needs to be to drive that. That sort of makes sense? Yeah. Okay, let's pause there then, because I don't want to dig into the specifics of that. I really want to kind of back away from the specifics and kind of pull back out to this issue of the higher level evaluation. So let's do that. Let's pause now. Come on back in 5, and we'll finish up by kind of taking a look at that issue of really, okay, given that all this works for doing the computation, what do we do with all these numbers? Okay, so let's do that.